Okay, so here's a second program that's a bit more challenging because it has a while loop in it. So it's a program that adds two numbers. So you have m and n lying around with some values, and these are inputs, and you want to execute. I mean, you run a loop that is going to leave the sum of m and n in m, right? And the way you're going to do it is you're going to decrement n and increment m, and when n is at 0, then m is going to be the value you want, right? So if you start at, where you have 2 and 2, then you go to 3 and 1, then you go to 4 and 0, and then you return 4. And the while loop will stop at 0, so it will stop when you're at 4 in m. So that's the algorithm here. Of course, it's a constructed example. I mean, this is not a good way to perform addition, especially that, I mean, if you have an addition operator like you have here, you can do it more efficiently. It's just to show the mechanics of, the whole machinery of a while loop and OR logic. So correctness is like this. You have, again, these, these 0 variables that freeze the initial state. Like here, you execute the add program, and at the end, you want n to be 0 and m to contain the sum of the two initial values, right? And then the trick is, well, we're going to use while intro prime, the one that's more convenient to use. And we use it directly, the whole program is a while loop, so we don't need to enter tactic mode and then perform an apply or something like that. We just use a proof term here. And here we need to choose an invariant. And the invariant we choose here is that the sum of those two variables should be the desired result at any time, right? So at first you have 2 and 2, but the sum is 4. Then you have 3 and 1, but the sum is 4. And you have 4 and 0, and the sum is 4. And in addition, you have that n is 0. So that means m contains the desired result, right? So that's the kind of thinking we have. So here the invariant is here, that, as I explained. And you have to choose the right invariant, or a right invariant has to be correct and has to be powerful enough, right? You could put true here, that would be a correct invariant, but wouldn't be strong enough. Okay, so there's a proof inside. I'm going to skip the details because this is mostly just straightforward, except here near the end where we have a -1 here. And you might remember when we want to reason about -1 with the natural numbers, 0 becomes a special case. So the best is to perform a case distinction, and then we can handle zeros especially. And in this case, well, finish can do the job. And here we use, actually things are not so bad, except we have this suck, not suck, which is very annoying. So here I use a lemma to replace it by +1, and then I use linear arithmetic. It would be nice if, I didn't need this part here, but linarit for some reason isn't smart enough to reason about suck. And then there are more proof obligations here, but they're very easy to discharge with contextual rewriting. You see these are very straightforward. I think their CC might not work, but I think, oh, CC works. Oh, that's nice. Yeah, I like those two. Oh, it doesn't work for the second one. But, maybe finish works, right? Let's try finish. And if finish doesn't work, then you can try Swedish. Just kidding. Any Swedes in the crowd? Oh, maybe one Swede. Yeah, let's see. Okay. But yeah, I think CC is a good call here. I'm torn. I like the symmetry as well.